Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Lydia Gilmore, who is a graduate student in mechanical engineering at the University of Maine. Lydia was UMaine's co-valedictorian in 2024, and she's studying textile properties for her graduate work. I've had the pleasure of knowing Lydia for many years, and it was a lot of fun to hear her talk about engineering and textiles with such passion. Our conversation was recorded in April 2025. I hope you enjoy it as much as I did. Lydia, welcome to the Maine Science Podcast. I usually talk to people who are way far along in their career or, years and years in, and I realized catching up with you at Natural Living Center and a couple other people, I was like, I am missing a whole really cool group of people who are early in their career. So I thought it would be fun to chat. And we can get into why I think you're the mesh between kind of what you're doing at UMaine and why I think your research is so cool. But before we do that, can you let me know what was it that made you decide mechanical engineering and engineering was the path you wanted to take?
Yeah. First of all, thank you so much for having me. It was so cool. You mentioned the podcast again at Natural Living Center, and I was like, oh, that's a really neat idea. So mechanical engineering, I've always been really strong in math and the sciences. Those kind of clicked for me. But I was also very good at the arts and I was very creative. And so engineering kind of seemed like a very natural meshing of the two. I've come to find out that it isn't always the case, but I think that coming into it with more creative point of view is actually really helpful. And a lot of it requires a lot of creativity and a lot of adaptability. So yeah, it actually ended up playing to my strengths pretty well, and it's worked out so far.
It's really interesting that you went in thinking that it would be a good match with artistic and creativity. So the deep, dark secret here for our listeners is that Lydia went to high school with my daughter. So I've known her for years and years, which is actually really fun. And I always just saw you more in the arts world, maybe because that's the world Claire was in, right? So I didn't think about the other world that you had. So what was it that made you realize that sometimes not everybody in engineering has the same creative approach?
Yeah, going to grad school was a huge thing. When you're in undergrad and you have all the fundamentals, your fluid mechanics, your thermodynamics, your strengths and materials, there's an equation and there's an answer. You reach that answer, and that's pretty satisfying on its own, I'd say. You can kind of get those skills. Once you start to hit grad classes and grad research, where you're kind of doing something new, you realize that, oh, those things were simple because those are steps and those are tools to do new things. And it makes complete sense now. I don't know why it didn't really click at the time, but I think my ability to adapt and have this, we need this to happen, make it happen. And all you have are just ideas floating around in your head. And all of a sudden it's your job to make it happen, which is really scary and really exciting. Like, this is a goal. These are some tools. These are some resources. Make it happen. And every single person in the office would make it happen in a completely different way. So I've hit roadblock where I need something to happen and I just don't know how to make it happen cheaply or in a way that is easy to do in a lab with the resources we have. And so I'll just knock on doors of the engineers, the PhD students, the other master's students, and go, this is what I'm working with. What would you do? And you get just the wildest ideas, but everyone would do it in a different way. And so your personal creativity actually plays a huge part when you're actually trying to do something new and trying to engineer, like use the tools that you learned in undergrad that you hopefully are strong in, that are very important, where like there is a correct answer to those things. It becomes really important to think outside the box, think, how can I repurpose something? If it was manufactured for one purpose, can I reuse it for my purpose? How can we use the things at our disposal to make something new happen? And that's actually really cool to me. So I've enjoyed that part of grad school.
I'm really glad that you mentioned the foundational part of undergrad. And I think it's really easy to forget that a lot of what you learn in undergrad is steps and tools and foundation, and how you figure that out is really important. And I didn't mean to imply that engineers don't have creativity. Just for anybody out there who's thinking I'm slamming that, I think it's just a very different approach than what I see in humanities and artists, just from the perspective of what you said, that you have to have foundational tools in a way that's different than what they have to, All right. So the research you're doing now, if I've got it correct, you're doing textiles work at the Composite Center.
Yes.
So dive in. Tell us what you're working on.
Yeah, so I can't talk about it in a ton of detail, unfortunately.
Broad strokes. We can do very broad strokes here.
Yes, very broad strokes. So it's rapidly deployable shelters using drop stitch panel. So I'm only going to share what is currently publicly published and what has been proposed in a publicly available paper by Bill Davids, my advisor. So drop stitch fabric is just what an inflatable paddleboard is made of. That's one example. So it's just an inflatable membrane, but you blow it up and it would want to become a circle like any other balloon or anything, but it remains flat and those two walls remain parallel because there are drop stitch yarns actually interwoven connecting those two sides. So there are hundreds or thousands, or there are different densities of drop stitch yarns keeping those walls parallel. And these panels, especially when inflated to higher pressures, can handle a lot of load. So they can handle a lot of load in bending, especially. And so my advisor came up with the idea to integrate those drop stitch panels into shelters. Because, if you have a shelter that you need to pop up out of nowhere, it's ideal for it to be light. It's ideal for it to be packable, transportable. It's ideal for it to go up with as few people as possible. So that's kind of the idea, is to see how we can integrate drop stitch panels into rapidly deployable shelters.
Is the stitching for the panels, is it a particular kind of material?
I don't think that the fibers have to be a specific type of material. The drop stitch is interwoven with those walls as well. So it's not necessarily stitched on, but you can weave it all at once. And the drop stitch fabric on its own can't hold air. You would have to then coat the outside with something that makes it impermeable to air so you can actually inflate it. But the drop stitch on its own, I've heard it called spacer fabric, things like that, but it just holds space. And then when you coat the outside of it, it can then hold air.
So you all are trying to figure out if this is a feasible approach for temporary shelters.
Yes.
Okay. Is this the kind of thing where you can no longer look at inflatable paddleboards the same way again?
Not yet. We have a year to go, but I still enjoy paddleboarding a year in, so.
Well, it's more like, do you look at it and think, I wonder what else we could do with this kind of material? Do you have that approach?
Not in the way of like, oh, no, not drops.
Yeah, not that. No, not in the banging your head against the wall thing yet. No, not that.
No, it's definitely really interesting. I think that it's probably underutilized in a lot of ways because the main example that I can ever think of when people ask what's drop stitch is an inflatable paddleboard or a lot of floating docks, inflatable floating docks you would put out on a lake or something are also drop stitch. And just because it has so much load bearing capacity in a lot of implementations, I'm surprised it's not utilized more. So yeah, it's definitely a good thing to think about. I don't know if future grad students will be implementing it in other ways, but that would be a cool idea.
So you have mechanical engineering bachelor's, and then this is for your master's degree work. How much of what you're doing crosses over into things like materials engineering? Or is it just, since materials you already know is really just testing the mechanical, and you don't have to talk about this project in particular, but in general, like how much do you have to worry about the materials, or has that work been done, or is it kind of a little fuzzy and going back and forth between the two?
So we're mostly looking at a very macro scale of behavior for the panels. And there are other grad students that I'm working with whose work has been cleared for public release. So that gives me a little bit more wiggle room, which is nice. But if you put panels in 4-point bending, for example, where you're supporting it on two ends and you bend it in the middle and you record that deflection and the amount of force you're putting into that, you can actually back calculate certain properties of the panel. And the properties of the fabric and the fibers you use are going to affect the properties of the panel. That's not necessarily the side that I'm working on currently. But I mean, if you wanted to create an optimized panel, you would look at how do those properties of the fibers and the coating and things like that, how does that affect, whatever you want your panel to do? And that would depend on what you're using it for. So if you're using it for a shelter, if you were using it for a dock, if you're using it for a paddleboard, how do you want that panel to perform? And then in effect, that comes from the material, but we're not necessarily making them right now. So we're just using things that are commercially available to us, or I know other grad students are having panels made by third-party companies with certain properties and then getting them shipped in. But yeah, you could alter the material that they were made of, and that would change their properties. And you could probably predict that with modeling, but you'd probably have to experiment a little bit to really nail that down.
So you have the cool job right now, basically, of an engineer who's breaking things to see what the pressure point is, right?
Exactly. Breaking things secretly. It's very fun. Yeah.
Well, actually, it must be pretty hard in some ways not to be able to talk in more detail about your research, partly because with you starting with a paddleboard as the material, instantly I'm like, ooh, cool. How about this? How about this? And so you must find it because you're starting with something that people know about now. And actually, I have thought about how strange it is that we have inflatable paddleboards and how great they are. It's almost like, where did they come from? It seems to have happened so suddenly. You know, if you live anywhere where people are outdoorsy, people know what that is. It must be frustrating for you in some ways not to be able to talk about it more.
Yeah, it's definitely hard when you want to talk about things more, especially in grad school, when you're going to, for example, design an experiment and it's going to go wrong at least once. And I come home and I'm talking to my parents, talking to my friends, and I'm saying, oh, like I'm trying this idea and it's just not working. And I'm so frustrated and I want to try this and maybe this, but I can't really talk about it in detail. And most of my friends and like teammates and family members have no idea what I'm doing. They're very supportive nonetheless. They're like, you go tackle that thing that you're doing. Good luck. And I'm like, thanks, guys.
One of my longest and dearest friends works at a national lab, and I don't know what he worked on, but I kind of had the same thing. Like, I hope it's going great.
Yeah.
Because you just can't talk about it, which is hard.
Yeah. In my case, it's a lot less exciting than it sounds when I'm like, oh, I can't talk about it. It's a secret. But I think it's pretty interesting.
So do you think you want to keep, and this is the conjecture part of our conversation. Do you think you want to keep going down this path of testing out new things to do with commercially available materials? I mean, mechanical engineering is so wildly wide open. There's so many parts of mechanical engineering. So I went to an engineering school for undergrad, actually graduate school too, and mechanical engineering was by far the most popular engineering. Hundreds and hundreds of mechanical engineers every year. And a lot of them were way into machines, cars, design for large manufacturing, things like that. But there's then what you're doing, which is a whole other feature of mechanical engineering. So do you want to keep doing that? Do you want to try something new? Do you have any idea?
Currently, no idea. With the camp of grad students that gets asked, how are you going to use your degree? That's a great question. Because mechanical engineering is so broad in scope, it's hard to really nail down what I want to do, especially because a lot of the engineers that I speak to that love their jobs will also tell you, I had no idea that my job existed before I found it, and I love it. So I'm also a little scared to narrow down my options too far and really shoot for a very niche field because my dream job, my dream field, I might have no idea that it exists right now. So I'm trying to keep that in mind. But I know when people ask, like, what's your dream job? What's your dream position? I tend to tell them, for example, designing running shoes, running technologies, that kind of thing for a company like New Balance. I just like New Balance. And we're a New Balance sponsored school for the track team. So that's why that's my top answer. And, a lot of spacer fabrics and things like that are also used in shoes, but there's the way that the foam deforms. There's a lot of modeling that needs to happen there. There's biomechanics, which is its whole other branch, which is like how the body works as a machine. And then you have to make this invention that takes how the body works as a machine and make it work as a better machine, things like that. So I think that stuff's really cool. But yeah, I'm not too quick to dive right into one thing. I'll stay pretty open, I think, till I graduate.
I think that's really smart. Speaking as someone who's doing something completely different than what my undergraduate or graduate degree was in. So I'm glad you mentioned New Balance and running. You've been a varsity runner at the University of Maine now. You're still on the team, right? You got the COVID year?
Yes.
Yeah, which is great. I think it's really fascinating to think about all the engineering and science that goes into sports in general, which way beyond what it was even 30 years ago. So while you're running, watching other people run, are you sometimes thinking about the actual mechanics and engineering of the shoes you're running on? Which is not a fair question for a college athlete because I know you're supposed to be working on other things, but sometimes you just can't help have your brain wander while you're doing some long training.
Yeah, a lot, actually. If you were to listen in on conversations on the team, we are constantly talking about running. What shoes are you wearing? What new shoes do you want to try? What new gel do you want to try? What new exercise is going to make your body move more efficiently? What invention is going to help you do that? Yeah, we really think about that nonstop. And we've seen the running community kind of go through a lot of trends too. There was the whole barefoot running trend where you wanted your shoes to have a wide toe box and almost no stack height at all, just really, really close to the ground. And then that worked for some people, didn't work for others. And now we're kind of seeing the Hoka type shoes or the New Balance Fresh Foam X More and just these super tall, squishy shoes running on clouds. So there's a lot of different answers to that problem, but I'd say a lot of runners think about it often. We have different shoes for different workouts, things like that.
Whether you're having a conversation with your teammates or not, do you think about it while you're running or while you're thinking about how best to train?
I do. I don't get into it as much as some of my teammates, I think, but I also just really enjoy the New Balance shoes that we get from the team. I haven't ventured too far outside of that, but I do think about it while we're running. If we're about to do something a little bit speedier, I might take off my cushy, comfortable trainers and put on something a little bit more rigid with a carbon plate for some more energy return, things like that. Something to feel more springy. If a race is coming up, I might think about if I want a spike with more stack height where it's a little bit squishier, a little more structured, or if I want something where I'm a little closer to the ground and I can grip the ground a little more and there's better energy return if it's, flatter and more rigid with a carbon plate, things like that. So I definitely do think about it. I don't know if most people would think of that as engineering, but there is so much science that goes into it and so much engineering that really does go into that stuff. Yeah.
I'm curious, did you hit a point where you realized that when you were thinking about this, it was almost the application of what you were learning in school?
Definitely. Engineering as a whole, it's just applied problem solving. And everyone has problems. Runners have problems. Athletes have plenty of problems. So, yeah, there are a lot of engineers that have worked on things like that. We've gotten the opportunity to talk to some representatives from New Balance who get feedback on prototype shoes and things like that we get to try out. And even if they themselves are not engineers, some of them have engineering backgrounds and they were college athletes because they need to know what the college athletes are talking about and they need to know what the engineers are talking about to be this go-between. So yeah, there's a lot of STEM, a lot of engineering under the surface there that doesn't always get the flowers it deserves.
I'm going to circle back really quickly. Can you explain what it takes to get a master's degree in engineering? I know you've got another year, but a lot of the people I talk to are, as I mentioned, pretty far along in their careers. So we don't dive into kind of the academic route except to say, yeah, you did that. What are you working on? But since you're in the middle of it and you talked about it a little bit more, it would be really nice to hear your take on what it is for you to get your master's, the kind of the steps and then how it's different than undergrad. Yeah.
So I assume it's a little bit different program to program, but at the University of Maine, for a thesis master's, because you can choose a non-thesis master's, if you're getting a thesis, which is what I'm currently going for, you need coursework, so graduate courses. They're just more applied learning than kind of the fundamentals that you took during undergrad. I think you need 8, I want to say, 8 in mechanical engineering. And then I think a certain amount of those have to be directly in mechanical. You can take some in civil engineering or electrical engineering or something like that. You can branch out a little bit. You have to take seminar, which is where you and your peers present the work that you're doing at some point before you graduate. So that's once a week. You do research. So you take thesis credits with your advisor. And your advisor is largely going to determine what you're actually doing. So you're probably going to know before you start that degree who your advisor is, and what work they have available for a grad student. And so the research part of it is definitely the biggest, most important part. You just dive into a project that you probably don't really know about. And that's kind of the whole point. I've learned from many, many people now that I've spoken to after saying, this feels like too much, this feels like too much. And they've told me it's supposed to be too much. If it wasn't too much, they were going to give you a little more until it was too much, because that's the point. And so currently, my job description is like researcher. I'm working in the lab. I'm coding. I'm also interacting with project managers. I'm heading my research, and you're kind of wearing all of these hats. You have to see what happens behind the scenes to make new ideas happen. And you have to know what that takes. And I've gone through the same event that every other grad student goes through, where I designed an experiment and I thought, yeah, I'll have this done by the end of the month. Months later, it was still happening. And everyone was just around me going, yep, that's how it is. And you just have to go through it and see how science has to happen, so that when you're out in the real world, you have this degree that's not just like, oh yeah, I took more classes and I went further into my area of expertise and everything. But I had to march through how scientific progress happens. And I had to experience every step, and I had to lead every step, with help from advisors and peers and things like that. But yeah, it's really diving further into the subject knowledge and then applying it through your research and really like proving yourself that you got into the nitty gritty. You did every step. You were rigorous about it. You might have had some slips. You saw why things can be really hard, why things can be really expensive, why things can take so long, and why that's necessary and important. And then, of course, you write it up in a thesis, and that's what you defend and all of that.
Yeah, and learning cool things all along the way, right? I think one of the things that is easy to forget, that sometimes what you learn is this project isn't going to work like this, and that's important to know so that other people don't go try to do it that way.
Yes.
I think most people know this, but you're not paying for graduate school, right? You're working in the lab and getting paid, or are you TAing? Like, it's not something where you're adding to a debt load here, right?
No, luckily not. I have a research contract with the Composites Center at UMaine, where in return for my work and my research on the project, I get a stipend and they pay for my classes, which is fantastic.
And it's not like you're living high on the hog here. I just want to make that clear.
No,
You're living as a poor graduate student, which is great, right? Like, you don't have to worry about paying your bills, but you're certainly not rolling in the dough.
Exactly.
Yeah. This is really cool, Lydia. I kind of love the idea of you taking materials that we know about and seeing if you can find new purposes for them. You said that you stepped into a project that was already ongoing. Did you shop around for that project, or was it, just kind of happenstance that you found it?
So I was a very lucky case that I don't know is the norm. I was pretty academically successful in undergrad, and so I kind of had this fall into my lap, which I don't think is the norm. And I was very, very lucky and fortunate for that to happen. I think towards the beginning of my senior year during undergrad, I think Dr. David stopped me in the hallway, just walked past me and went, "Oh, by the way, are your grades good right now? Are you thinking about grad school? Okay, I'll send you an email." Cool, cool, cool. And it was this very quick conversation. And I reached out, and he explained about as much as he was allowed to explain to me before, signing my life away to get all the secret information. But he explained the concept about as much as I explained to you. And I thought it was really interesting. Because I wanted to move into the general direction of textiles, I thought that this was a really cool opportunity. The Composite Center also has a brand new, still like getting up and running textiles lab, which is really, really cool. And I really wanted an excuse to go in there. And now I have one, which is awesome. But it was just in the right direction of where I wanted to go. And it was something that was completely new and really interesting to me. So I was very lucky. It very much came to me in the hallway on a random Tuesday. So that was my experience. But I know most people shop around with their professors that they either know from undergrad or that they are seeking out at another grad school. and you can usually see what kind of research professors are doing. They're usually published, and you can kind of shop around and see what area you want to go into.
I agree that you were lucky, but you also put yourself in that situation by working pretty hard. So don't dismiss the amount of work that you put in to get there. You do have to make your own luck sometimes. Lydia, this has been a great conversation. I'm hoping we opened up a little bit of people's kind of like behind the curtain of what happens, how people figure out a little bit how they want to do engineering, and then also what it actually takes at the beginning of a career to get it going. I've really enjoyed this conversation. Thank you.
Yeah, thank you so much. This has been so much fun.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by following us on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. The Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. And the Discover Maine theme was composed and performed by Nick Parker.